At the end of the last video, I introduced a list of the types of stability around a steady state for pairs of linear autonomous equations. I want to go through those in detail. So these are the only 6 behaviors that can happen for a pair of linear differential equations. For nonlinear differential equations, all bets are off, all sorts of things can happen. But this at least will start to give you a flavor of what to expect when drawing these systems, these nullclines, these trajectories. So I'm going to put the steady state in the middle here, and it's the intersection of a vertical and a horizontal nullcline. One of these is from F and one of these is from G. Say I draw the arrows and all the arrows end up pointing towards the point in the center. The diagonal arrows in the regions and also the arrows on the nullclines themselves. If all of the arrows point towards a steady state, this is the most ideal stability. This is called a stable focus, and everything just tends towards a steady state. That means anything in this region, both P and Q, P is again the x-axis and Q is the y-axis, both functions are going to want to tend towards this steady state. It is completely stable and in the most straightforward way possible. If I draw the paths, this means that if I start somewhere in the phase plane, each point in the phase plane corresponds to a starting value for P and Q, then I'm going to end up on a path that goes towards the steady state. It may be a straight path, it may be a curved path, I don't exactly know, but it's going to be a pretty direct path towards that steady state. The opposite is an unstable focus. If I have a steady state here in the intersection of two nullclines and all the arrows point away, this is the most simple unstable steady state. So this is like the top of the hill situation, where if you have something imbalanced at the top of a hill, it's not going to move, but if it moves a little bit away from the top of the hill, it's going to roll down and away from the top in all directions. That's the instability of an unstable focus, all the arrows pointing away. And if I look at the trajectories, the paths that fit those arrows, I'm going to have paths, either straight lines or curved lines, that go away from my steady state. Those are the trajectories I expect. Something that's completely new in phase planes that phase lines didn't really have is the idea of a saddle point. So say again, I have nullclines, a vertical and a horizontal nullcline that meet at a point. That point is a steady state. And say I have a pair of arrows going towards and a pair of arrows going away, and on the nullclines I sort of have behavior that matches up with those two things. This is called a saddle point. From certain directions this is stable. From this diagonal everything's going to go towards this point. But from other directions this is unstable. Everything's going to go away. So I have sort of behavior that depends on the directions. What kind of trajectories do I expect? Well, in this diagonal where it was attractive, I expect paths to come in towards the steady state. But as they get towards the steady state, I expect them to diverge and start going away on the other diagonal, which was the diagonal where the arrows were pointing away. Unless something is perfectly lined up, almost all of these paths are going to be sort of reflected, swerved away from the steady state. And that's the behavior around a saddle point. I have 2 more types of stable and unstable situations. Previously, I talked about a stable and unstable focus, where things pointed directly towards or away from a steady state. There are also stable and unstable nodes. In this situation, the lines in the region, the arrows in the region, don't actually point towards a steady state or point away. They sort of are going tangentially around the steady state. But the lines on the nullclines are pointing towards. What you get out of this is you get spirals inward. So for a stable focus, we got more or less straight lines inward. We can also have spirals inward. That happens with phase plane with linear systems, where P and Q are both going to end up going towards the steady state, but doing so in a sort of weird oscillating manner in a spiral inward. And likewise, if I have these same trajectories that are going around, but on the nullclines I have lines away, I expect outward spirals. This is an unstable situation, but instead of just repelling things directly, it's going to sort of repel things in an oscillating, spiraling, swirling kind of shape. And the last behavior is the situation where all of these directions are sort of tangential. And this is called a center, And this is a situation where it's neither going towards or away from the steady state, but it's in perfect orbit around the steady state. And orbit is a good word because sometimes if you want to talk about differential equations that describe planetary motion, you can do it in exactly this way, and hopefully you should get centers. You should get trajectories that just spin around, neither getting closer nor far away, but in a perfectly stable kind of orbit. This also is a kind of stability. It's not a stability in the same sense that it approaches the steady state, but it is a stability in the sense that it is consistent. And this is called a center. Those are the only 6 behaviors that we can expect for linear systems, which is really lovely that they can be nicely classified into these 6 situations. As I said before, nonlinear systems can have all sorts of other qualitative analysis.